So last time we talked about why perhaps would we want to use layout control. And we define it as a control system for the whole layout that uses a communication bus network. So this time, what we're going to do, what we did last time is we defined the layout control network bus in general. We talked about two general bus configurations, why we might use them, but almost as important, why you wouldn't need an LCC or a layout control bus for your layout. And we want to make that point just in case there's some temptation to jump on the hype over layout control. So tonight what we'll do is we'll finish up by talking about how I use layout control on my particular layout, and then perhaps a quick summary. A little bit about me. I've been modeling since the 60s, primarily N-scale. I built my DC system, and I also built a 9-node CMRI layout control bus system for an operating layout. I want to reiterate what I mentioned last time. For me, this is a complex subject potentially. It's relatively technical as a modeling subject. But for me, my perspective is I'm not a computer hobbyist. I'm not an electronics hobbyist. I'm not a computer programmer by any means. I'm simply a model railroad layout builder who decided some features I wanted, had a need, and found a way to accomplish that. Again, now we talk about LCC more in general, but LCC, one thing we want to note is the NMRA made a very specific standard that they call LCC, but the layout control network is a fairly large tent of other possible solutions the model railroader could use. Here are some of them listed. But what I'm going to talk about is my particular choice was the CMRI system, which has an NMRA called CMRI net. It has an NMRA standard, but it's somewhat outside of the LCC definition right now. But the reasons I chose CMRI for myself was, number one, CMRI has been around and operating on layouts since the 80s, at least. So it has a long track record. It has incredibly good documentation. If you look at my 3 volumes on the left picture, each of those volumes is an inch thick. Now, for some, that's somewhat off-putting. For me, especially with my work background, when I can go find an answer or dig into an issue deeper, it's much better for the way I work. The other thing I liked about it was do it yourself. If you look at the right-hand picture here, you can see that you purchase very high quality industrial grade circuit boards, but then you populate those boards with the discrete components yourself. So you can pace yourself, you can learn as you go. You don't have to front a whole bunch of money out front. And then the last reason I chose CMRI was it's extremely versatile. Anything that I can think that I might want to control remotely or automatically, we can do with a system like this. CMRI basically is a serial-based communication network. It's RS-232 converted to 485 that gives long communication distances. In the case of a layout, you're not going to need much more than the easy 1,000-foot of communication bus that the CMRI allows with 485 serial. It utilizes what we call dumb nodes, in that there's no programming located at the node. So when you make changes, you don't have to program each node separately. And in my case, I have 9 nodes. It does require a host computer because it's in a master to slave polled configuration. And like we discussed last time, what that simply means is the master computer polls for the inputs from the slave nodes throughout the layout. It then takes those inputs and calculates what to do with them, and then sends output instructions to each of the nodes to accomplish the various tasks that the model railroader asked to be done. Again, we distribute nodes on a layout because you want to minimize wire runs and you want easier troubleshooting. So devices and discrete components are connected directly to their serving node, and then that node is on a communication bus. Here's some examples. I have 9 nodes, some pictures of the general configuration. Now, I was deliberate not to go into how this stuff is wired up, how it's built, how it's all hooked together, but this gives you an idea of what can be involved in a layout control network, and specifically CMRI in my case. There's a lot more wiring under the layout than the layout might give away. A typical node starts with a serial I/O card. It handles the communication from the master computer, and then it distributes messages for its particular address to output ports and reports to the host computer through input ports. So the center card there, it's a super mini node in CMRI terminology. It has 48 output lines and 24 input lines. If you look at the input side, I color code my inputs orange so that at the node, it's very quick to identify what's going on. And you can see also included right next to the inputs is a motherboard with 12 track detectors. And they're collated here at the node, and I interrupt the south rail of the DCC booster is where those are wired through, although they're not hardwired with a pulse transformer type decoder or detector, but they're wound through on the south rail. Then on the left side, you've got blue indicating outputs for items such as the switch motors, obviously LEDs and panel lights on fascias and valances, and as well your signals. Those are generally outputs. Now there's twice as many outputs on a node as there are inputs, because that ends up being what most model railroads typically use, a lot more outputs than inputs. Then each node has a converted computer power supply. Computer items such as these nodes need stable, consistent voltage, meaning as the current increases or decreases, you can't have that voltage dropping because computer chips don't like that. So we use converted power supplies as a very cheap and convenient source of 12 volt, 5 volt, and 3.3 volt where as necessary. And LEDs love 5 volts or 3.3 volts, by the way. So what do I use CMRI for? What do I use my layout control bus for? I won't go into everything, but I'll highlight some of the main features I do. Number one, I use it for signaling. That's pretty obvious. But with that signaling, I have the benefit of, for example, one-click change from route type signal architecture to speed type signal architecture. And for those that are aware of prototype signaling, route signaling has slightly different aspects displayed to the train crew for a given rule book. And there are different rules as to what the crew does with that information that the aspect conveys. Route signaling in general is a West Coast or west half of North America type of signaling, and speed signals are generally, and this is general, are generally found on the East Coast or east of the Mississippi. In addition, we have call on or return to train signal modes, whereby rather than the dispatcher having to clear a control point every time a switch engine needs to make a move, he can set it to call on, move, and the signals will automatically change as necessary as that switch crew moves back and forth through the control point. There's other features such as fleeting mode. Fleeting is where you want multiple trains heading the same direction in, say, 251D territory, where you have two-way traffic, but you don't want the dispatcher to have to clear signals every time a train goes by. So imagine in the case of a busy commuter rail situation where that traffic during rush hour can automatically clear as trains pass in one direction. So in addition to signaling, I utilize the bus is perfect for more complex track control. For example, NX plants. I have 3 NX plants on the layout, which are, it's a term the railroads use for entrance exit. They're more complicated interlocking plants that have multiple ways to get into the plant and multiple ways to exit the plant. So this automates, if you look at the picture in the lower left, you can see the yellow buttons. A train entering from the left needs to go to the yellow button exit on the right. It's an eastbound train, and that's all the dispatcher has to do is hit those 2 buttons and then release the signals, and it will reserve and align that route through the plant. That particular NX has 21 possible routings. In addition, simple interlocking, such as a single passing siding, is considered an interlocking in CTC. That is available for logic, whether or not to release a train or not. And then I use, for complex track control, I have automated staging ladder control as well. In addition, you can add other things, like I have my phone system is integrated. It's a party line system, but the control panels are designed to work on the bus so that you know who's calling you, you know who you want to call. And the system, one of the priorities was that when someone buzzes a phone, the computer sees it and will limit how long that buzz goes on so it doesn't drive us all crazy. In addition, we have automated staging control. It's dispatcher controlled. And once the dispatcher clicks on a button, certain things happen with automated staging. I'll go into a little bit of detail on that, but we don't have time for a full explanation. Then again, prototype turnout control, the last item on here. Now, when we talk about prototype turnout control, we're not necessarily talking about the scenery aspect, like we're using realistic ground throws and switch stands. What we're talking about is how the switch crews and the dispatchers interact with controlled turnouts or switches on the main line and on controlled track, and how the system integrates locking logic before those turnouts are allowed to be activated. First, let's talk about the automated staging. On the dispatcher panel, when he opens up the e-staging yard, all he has to do is click one of the little red buttons for the track he wants a train to leave staging to come onto the layout. The system checks for ladder occupation. Then if it's clear, it aligns the ladder, because that's a fairly complex ladder for almost 12 tracks. Then the system, through relays, turns on the track power so that the locomotives don't have to sit in staging running. We generally don't want that, especially with sound locomotives, if we can avoid it, because that's a total draw on the DCC system, as most of us know. And then lastly, if all's checking well, it launches the train and it talks to the DCC system and says, okay, start this train, turn on the sound, and accelerate slowly for 12 inches, and then accelerate again. And then the train arrives on the layout, the model portion of the layout, and the system automatically stops the train. To do that, if you look under this staging yard, it's raised up to the ceiling right now. You can see we've got the track power relays here on the right. The computer, through those relays, activates the DCC power to the tracks. Then you've got the switch motor control card on the left. The computer talks to those control cards, and they in turn tell which switch motor to move when. There's the tortoise switch machines arrayed underneath. And of course, in N-scale, like I mentioned before, you have to be careful because your distance between points is very small compared to, say, HO. So you have to carefully plan switch motor layout underneath. Then lastly, both of my 12-foot long staging yards are lifted when not in use up to the ceiling with an electronic lift. That way the wife can get to her storage room, or I would be in trouble. I haven't made that land grab yet. So I lift both of my 12-foot staging yards up with lifts. So now let's talk quickly or briefly about prototype turnout control. I'm using 4 primarily logic integrated types of turnout control that to simulate what the real railroad would do, starting with the hierarchy of power only. With power only, they're set up where only the dispatcher can throw those points. So in my case, I use them for staging yards. I'll use them for very critical junctions where the traffic has to be monitored carefully by the dispatcher. There are no provisions for line side control by a local crew. It's all by dispatcher remotely. Dual control, on the other hand, has provisions for both line side control and dispatcher control. And by default, those control points are under dispatcher control. But it has allowance for a crew to take manual control of those turnouts. Then the railroad has what's called automatic electrically controlled turnouts, whereby they've decided there's a case where a particular turnout near mainline controlled track is an additional hazard. And I'll explain briefly how that works and how the layout control bus helps me accomplish that. And then lastly, I'm using padlock only, whereby the turnout has to have a key or the computer won't allow those points to throw. And those are used on secondary but controlled sidings, for example, where speeds are slow and a switch crew is working. The benefit of prototype turnout control I have found after using it for quite a while is that it does add realism. And it helps us avoid operator errors. No one wants to throw turnouts inadvertently under a moving train. Again, for this type of prototype activity with control points, dispatcher involvement, and line side prototype turnout control, the system has to utilize and works with prototype locking protocols. So every time an action is requested by the dispatcher, the system runs through locking protocols to see if it can unlock and allow that request. Software is really the only way to do that, especially on a model railroad. Again, this diagram here, a simple passing siding to a controlled siding is considered an interlocking and will work these 5 basic protocols every time a move is requested or a signal is requested to be cleared. So let's talk about dual control. A dual control turnout found generally in CTC territory at a control point where the railroad has decided that not only is the dispatcher need to control those points, there is a case to be made where a switch crew is going to operate back and forth through that control point. So the railroad provides trackside control of those motors. In order to do that, I've laid it out for operators in a 4-step process. The first thing is you call the dispatcher and you get permission to take that turnout in hand. Then once you've been granted permission, you insert the key, throw the toggle off motor mode into hand mode, and those are the terms that the railroads use. So now the dispatcher doesn't have motor control or remote control of that turnout, the line side crew does. And then the crew can toggle reverse normal as they see fit to get the work done. When the work is done, then they notify the dispatcher after they remove the key, set both toggles to motor and normal, and then they move on. And those types of controls actually do exist in a dual control turnout motor situation. We don't have time to go into the locking logic, but there's a number of things, whether the turnout is in motor control from the dispatcher or whether it's been taken into hand by the switch crew, that the system's going to look at before the system's going to allow those points to be moved. Things like, is time locking active? Is there a key request already? Is the control point occupied? Is the throw already normal or reversed? And then when the signals are integrated into the decision, there's a whole bunch of other decisions that the system is going to be making prior to allowing that crew to throw those points. In a model railroad environment, that's a matter of seconds. In the real railroads, it may be longer depending on how the circuitry is set up. Again, with centralized traffic control and automated or prototype turnout control, dispatchers and train crews don't make the decisions. The system does. All we can do is request those moves. And that's to keep the humans from being humans and making human mistakes. Now, another type of turnout control I'll talk about briefly is that automatic electrically locked turnout, which is not widely known or used in model railroad layouts, but it has pretty cool play value. And it has some actual, I mean, if you've got a quite valuable brass set of locomotives and train that you would really not like to have derailed because someone else pulled a train out in front of you and fall to the floor. I mean, there's practical uses besides the safety uses that the prototype would use. So in the case of an automatic electrically locked turnout, what the railroad is doing is saying, hey, we have a case where we've got a relatively high-speed main line, and we've got a spur emanating off of that main line. And if the main line is 20 miles per hour track speed or higher, we have to have a way of protecting from someone opening the points in the face of an oncoming train. Now, some railroads will, to avoid putting in an automatic electrically locked turnout, will actually require by rule that no train may totally vacate the main line on a spur. And by not allowing that, it means that at all times that track section would be detected as occupied. But in this scenario, say this is a large industrial park, and that train has totally left the main line to go work that industrial park. When that crew comes back to re-enter the main line, we have to have some kind of protection to keep them from opening the points and pulling out onto the main in the face of an oncoming train. So the automatically electrically locked turnout has provisions for logic before that crew can open the points. Is the next CP east or west occupied on either ends of that track section? Is there time locking westbound or eastbound? Is there already a train reserved by the dispatcher and the dispatcher simply forgot? Then the release logic, once the crew requests that set of points be opened, is the key request made? Is the timer already active? Is there a release section occupied? Is the main occupied? These kind of things are what the system is going to look at. Again, the operators, for my layout, it's a 4-step process. You call the dispatcher, say you want to take the points. Then you insert the key, and what the crew's waiting for is that yellow LED to illuminate after the system runs time and the checks it needs to run. And I've programmed in a 20 to 30 second delay. Typically in the prototype, you may have a 10 to 30 minute delay. And that's to allow, in case a dispatcher does send a train down the main and it was late, or there's some other extenuating circumstances the dispatcher may have forgotten about, the system will know and prevent the points from opening. Then once the light is lit, the crew can toggle reverse and normal at will. So here's the scenario where the interlocking logic, the locking logic, protects the crew. In the case of, well, it would be obvious that the crew might be hearing that train coming, but let's say the train is pretty far away around the mountain, the crew can't see it, can't hear it. You can see where if they're not protected, they could inadvertently, if the dispatcher forgot that he had already reserved that track, they could inadvertently open those points. So the green indicates on a dispatcher screen that that track is already reserved. So the system knows that it's not going to allow that LED to come on. Now, a little enhancement for additional realism, most electrically locked turnouts have what's called a release section in the prototype. It's a section roughly 100 feet from the points that is individually detected, and it will know then if a train or part of a train is on that section. What it actually does is gives the crew an immediate release where as soon as they key, they can move the points. So the assumption by the system is if there's a train there, that it's a switch train that needs to do work. And so it's going to grant the release right away. And so I program that into my electrically locked just as another fun toy. So well, that's your scenario. That's where if the crew knows to pull into the 100-foot release section, they'll get an immediate release as soon as they get permission and open the padlock. So that describes briefly 4 types of turnout control. So between the signals and the signaling modes and complex track control, and now prototype turnout control, I've got a little bit more realism that pretty much, in my opinion, only a layout control bus with software can do to enhance the fun. So that was an overview, brief overview. We don't have much time to go into much more, but I wanted to show you a few things that I do with a layout control bus and how it enhances our enjoyment of the layout. And I've incidentally found that as complex as it may seem some of those features are, that my young grandsons, for example, adapt almost immediately. And it's probably because they don't bring a preconceived notion of how things should be on a model railroad layout when they walk into the layout room. So they adopt to the system pretty quickly. So in summary, we talked about why, but as just as importantly, why we might not need a layout control bus. In addition, complexity is okay for the builder and the layout designer, but it's bad design if it ends up being complex to operate by the guests and the operators. So that is something I put into everything I tried to do. I certainly don't want operators in the layout room that are confused, having a hard time trying to figure out a very complicated system. We have found that it's not very complicated at all, except for the builder. And it doesn't take that much extra effort to get 90% through software if you've already got the hardware and the signals in place, for example. And that is pretty much it, Jim.